The core of the Sun is 15 million degrees. That sounds violent, unimaginably hot, a furnace beyond anything on Earth. But in 1929, two physicists ran the numbers and discovered something unsettling. It is not hot enough, not by a small margin, not by a factor of 2. The Sun is roughly 200 times too cold for its own fuel to ignite. Classical physics says every single proton collision in that core should fail. No fusion, no light, no warmth reaching any planet anywhere. For decades, nobody could explain how the stars stayed lit. Then, a young physicist named George Gamow showed that the barrier between two protons was not as solid as it appeared, that particles had been walking through walls since the universe began. What he uncovered is called quantum tunneling, and it does not just power the Sun, it writes data onto every flash drive on Earth. It reads surfaces atom by atom, and it is rewriting your DNA right now. Today, we trace it from the mathematics that revealed it, through the interior of every star, to the living code inside your own cells. If you enjoy deep dives like this, a like or subscribe genuinely helps the channel grow. The journey is a long one. Let us begin. There is a rule so basic, so deeply embedded in how we experience the physical world, that most people never think to question it. A wall stops you. A hill, if you do not have the energy to climb it, turns you back. A locked door stays locked. This is not philosophy. It is everyday life, confirmed by every interaction you have ever had with a solid object. And at the scale of the world you can see and touch, it is entirely correct. Classical physics agrees without hesitation. If a particle does not carry enough energy to get over a barrier, it bounces back. Every time. No exceptions. The mathematics of Isaac Newton and the centuries of mechanics that followed leave no room for ambiguity on this point. The barrier wins. Except it does not. Not always. Not at the smallest scales. In the early 20th century, physicists discovered something that violated every classical intuition about how matter ought to behave. A particle, an electron, a proton, an alpha particle could arrive at a barrier carrying less energy than the barrier demanded and still appear on the other side. Not by climbing over, not by breaking through, by passing through the barrier as if on some fundamental level the wall simply was not entirely there. This is quantum tunneling, and as Gamow showed, it is not a rare or exotic event. It has been happening since the first atoms formed, at scales too small to see, in processes that hold the universe together. The probability that a particle will tunnel depends on three things: the height of the barrier, meaning how much energy the barrier demands; the width of the barrier, meaning how far the particle must travel through it; and the mass of the particle itself. Increase any one of these, and the probability of tunneling drops. Not gently, exponentially. A barrier twice as wide does not halve the chance. It can reduce it by a factor of millions. This exponential sensitivity is the defining feature of the phenomenon, and it is the reason tunneling behaves so differently depending on what is doing the tunneling and what stands in its way. For electrons, with their extraordinarily small mass, tunneling through barriers just a few atoms thick is routine. It happens constantly in the natural world and has been engineered into technologies you use every day. For protons, roughly 2,000 times heavier, tunneling is far less frequent, but still common enough to reshape the workings of stars and even the chemistry of living cells. For anything heavier still, the probability collapses. A tennis ball hitting a wall has a quantum mechanical probability of appearing on the other side. The mathematics permits it. But the number is so vanishingly small, so incomprehensibly close to zero that you could wait longer than the current age of the universe and never see it happen. Not once. So tunneling belongs to the realm of the very small, but its consequences, as we are about to discover, are among the largest in the known universe. To understand why it happens at all, you have to be willing to let go of a picture that served physics beautifully for centuries. The picture of a particle as a tiny solid object, a miniature ball with a definite position, moving along a definite path. That image, inherited from Newton, is intuitive, satisfying, and at the quantum scale, wrong. A proton is not a point. It is described by something called a wave function, a mathematical object developed by Erwin Schrödinger in 1926 that encodes the probability of finding the particle at any given location. Where the wave function is large, the particle is likely to be found. Where it is small, the particle is unlikely to be found. Where it reaches zero, the particle will not be found at all. It was Max Born, working in Göttingen, who gave this wave function its physical meaning. The square of its value at any point gives the probability of the particle being there. And this was not a statement about ignorance, about scientists simply not knowing where the particle really was. It was a statement about reality. The particle genuinely does not have a single definite position until it is measured. This remains one of the most unsettling truths in all of physics, and it is the foundation on which tunneling rests. Now imagine this probability wave approaching a barrier. In the classical picture, the story ends at the wall. The particle does not have enough energy, so it turns back. But the wave function does not abruptly stop. It enters the barrier and begins to decay, shrinking exponentially, getting smaller and smaller the deeper it penetrates. If the barrier is thin enough and the particle light enough, the wave function has not quite reached zero by the time it emerges on the far side. A small, non-zero amplitude survives beyond the wall. That residual is everything. A non-zero wave function on the other side means a non-zero probability of finding the particle there. Not a certainty, not even a likelihood in most cases, but a real, measurable, physically meaningful chance. And when you repeat the experiment with billions of particles, or wait long enough, that small probability becomes an inevitability. There is another way to approach this, through Werner Heisenberg's uncertainty principle. Energy and time, in quantum mechanics, are bound together by a fundamental limit. The shorter the time interval you examine, the less precisely the energy can be defined. For very brief moments, a particle's energy is not a fixed number. It fluctuates. During one of these fleeting intervals, a particle can, in a sense, possess enough energy to exist within the barrier. It does not violate conservation of energy. It exploits a deeper truth about the nature of measurement at the quantum scale, a truth that has no parallel in the everyday world. The standard mathematical tool for calculating how likely a particle is to tunnel through a given barrier was developed independently by three physicists in the late 1920s. Gregor Wenzel, Hendrik Kramers, and Lodin Brillouin each arrived at a method, now known by their initials, that gives a transmission coefficient. This is a number between 0 and 1, describing the fraction of incoming particles that make it through. The formula confirms what the physics demands. The coefficient drops exponentially with barrier width, barrier height, and particle mass. Change any one of these, and the odds shift by orders of magnitude. It is worth pausing here for a moment to absorb what this means. Every tunnel event that has ever occurred, every alpha particle that escaped a nucleus, every electron that passed through an insulator, every proton that shifted position within a strand of DNA happened because the wave function of that particle did not obediently stop where classical physics said it should. The mathematics is precise, testable, and confirmed beyond any serious doubt. The discomfort it produces is not a flaw in the theory, it is a flaw in the intuition we built from living in a world of large, heavy objects where tunneling probabilities round to zero and walls behave exactly as we expect them to. Tunneling is not a glitch in the rules. It is not an exception granted to small particles by some special clause. It is a direct, unavoidable consequence of describing matter as waves rather than points. If particles were truly hard little spheres, tunneling could not happen. But they are not. They are probability distributions spread across space, and the mathematics of waves does not respect a wall the way a ball does. By the early 20th century, physicists had a problem they could describe with extraordinary precision, but could not explain at all. Ernest Rutherford's famous scattering experiments, conducted with Hans Geiger and Ernest Marsden in Manchester, had revealed the internal structure of the atom. At its centre sat the nucleus, tiny, dense, carrying a positive electric charge so concentrated that it created an enormous electrostatic barrier around itself. This barrier, called the Coulomb barrier, acts like a fortress wall. Any positively charged particle approaching the nucleus is repelled with tremendous force. The closer it gets, the stronger the repulsion becomes. To reach the point where the nuclear force takes over, the short-range attractive force that binds protons and neutrons together, an incoming particle must carry enough kinetic energy to push through that electrostatic wall. The mathematics here is not ambiguous. For uranium-238, the Coulomb barrier stands at roughly 8.57 mega-electron volts. An alpha particle, a clump of 2 protons and 2 neutrons, emitted naturally during radioactive decay, would need at least that much energy to escape the nucleus by climbing over the barrier. And yet, the alpha particles that uranium emits carry only about 4.2 mega-electron volts, less than half of what the barrier demands. This was not a subtle discrepancy that could be waved away by measurement error. The particles were leaving the nucleus with barely half the energy required. They were getting out, reliably and repeatedly, through a wall they had no classical right to cross. Rutherford himself struggled with the problem. He and others proposed models, satellite orbits, oscillating internal structures, mechanisms that tried to explain alpha emission without abandoning classical physics. None survived scrutiny. The numbers refused to cooperate. Making the puzzle stranger still was the relationship between the energy of the emitted alpha particle and the time it took the parent nucleus to decay. In 1912, Hans Geiger and John Nuttall catalogued a range of radioactive elements and discovered a pattern so tight it almost looked engineered. The higher the energy of the alpha particle, the shorter the half-life of the nucleus that produced it. This held across dozens of isotopes, and the relationship was not gentle. It was ferociously steep. Consider the extremes. Thorium-232, whose alpha particles carry a relatively modest energy, has a half-life of roughly 14 billion years. That is approximately the current age of the universe. Polonium-212, whose alpha particles carry only somewhat more energy, has a half-life of 0.3 millionths of a second. Read that again. A factor of roughly 2 in the energy of the emitted particle. 16 orders of magnitude in lifetime. The difference between the age of the cosmos and a flash too brief for any human sense to register. Geiger and Nuttall had given physics a phenomenal empirical law, a stunningly precise relationship between energy and half-life that held up across element after element. But they had no mechanism. They could plot the curve with beautiful accuracy, yet they could not explain why it existed. For more than 15 years, the Geiger-Nuttall relationship sat in the literature as one of the great unsolved puzzles in nuclear physics. The data was immaculate. The explanation was nowhere. The answer arrived in the summer of 1928 from two directions at once. George Gamow was 24 years old. Born in Odessa, trained in Leningrad, he had travelled to Göttingen, the German university town that had become, almost by accident, the intellectual capital of quantum mechanics. Max Born ran the Physics Institute. Werner Heisenberg had recently passed through. The influence of Niels Bohr radiated from Copenhagen, just a short journey north. Göttingen in the late 1920s was where the new physics lived, and Gamow had come to immerse himself in it entirely. He was not the first to notice that quantum mechanics might explain how particles could pass through barriers. A year earlier, in 1927, Friedrich Hund had applied the idea to molecular physics. Working on the spectra of molecules like ammonia, Hund showed that a particle trapped in a double well potential, two energy valleys separated by a barrier, could appear in either well without the energy to climb between them. The wave function leaked through the dividing wall. It was an elegant result, mathematically clean, and it solved a real problem in spectroscopy. But it remained a quiet finding, confined to the world of molecular physics, and almost entirely overlooked by the community working on the nucleus. Gamow saw further. He took the tunneling concept and aimed it directly at the problem that had baffled Rutherford. With mathematical assistance from Nikolai Kochin, he set up the Schrödinger equation for an alpha particle sitting inside a model nuclear potential. The setup was a deep well of attractive nuclear force, surrounded on all sides by the tall, repulsive Coulomb barrier. Classically, the alpha particle is trapped. It does not have enough energy to climb the wall, so it stays inside forever. But the wave function does not obey classical rules. Gamow's solution showed exactly what the theory predicted. The wave function of the alpha particle decayed exponentially inside the Coulomb barrier, shrinking as it penetrated deeper, but it did not reach zero. On the far side, a residual amplitude survived. The alpha particle had a finite probability of appearing outside the nucleus, free and clear, without ever having climbed over the barrier. The beauty of the result was not merely that it explained alpha decay, it explained the Geiger-Nuttall law. Gamow's formula expressed the tunneling probability as an exponential function of the ratio between the barrier height and the particle's energy. A small increase in energy changed the exponent, and because the relationship was exponential, even a modest shift in energy produced a colossal change in the transmission rate. This was exactly why a factor of 2 in alpha particle energy could produce 16 orders of magnitude difference in half-life. The exponential sensitivity of quantum tunneling was the missing mechanism, and it matched the empirical data with remarkable fidelity. What Gamow did not know, working in Göttingen that summer, was that an ocean away, two physicists at Princeton had arrived at the same conclusion entirely independently. Ronald Gurney, a young British experimentalist, and Edward Condon, an American theorist, submitted their paper on the 30th of July 1928. Gamow had submitted his the day before. Neither group had any knowledge of the other's work. The convergence was pure coincidence, and it gave the result a weight that a single paper, however brilliant, could not have carried alone. Two independent lines of reasoning, using the same new physics, arriving at the same answer within 24 hours. It was as close to proof as theoretical physics gets before the experiments catch up. There is something worth noticing about how this discovery unfolded. It didn't come from the most senior or most celebrated physicists of the age. Gamow was 24. Gurney and Condon were working outside the major European centres of quantum theory. Friedrich Hund, who had glimpsed the idea first, never received widespread recognition for it. Quantum tunnelling was not handed down from established authority. It was found by young minds working at the edges of a theory that was itself barely 2 years old, and its true power only became apparent as the consequences accumulated. It took a few more years for the phenomenon to acquire its name. The German word came first. Walter Schottky used Wellenmechanischer tunnel effect in 1931. The English term, tunnel effect, followed through Yakov Frenkel in 1932. The metaphor stuck because it was almost physically accurate. The particle does not go over the barrier. It does not go around it. It passes through, as if a tunnel existed in a wall that classical physics insisted was solid. Here is the fact that makes tunnelling more than a nuclear curiosity. Without it, the sun would not shine. No star in the observable universe would ever have ignited, and every planet orbiting every star would be a frozen rock drifting in permanent darkness. In 1920, the British astrophysicist Arthur Eddington proposed something radical. The energy source of the sun, he argued, was not chemical combustion and not gravitational contraction, but nuclear fusion, the conversion of hydrogen into helium deep within the stellar core. His colleague F.W. Aston had recently measured the masses of hydrogen and helium atoms with enough precision to reveal a discrepancy. 4 hydrogen nuclei weigh slightly more than a single helium nucleus. The difference is small, but when converted to energy through Einstein's equation, energy equals mass. Times the speed of light squared, it is enormous. Enough in principle to power a star for billions of years. Eddington was right about the energy source, but he had a problem he could not solve, and he knew it. For 2 protons to fuse, they must first get close enough for the nuclear force to take hold. But both carry a positive charge, and at short range the electrostatic repulsion between them is immense. The Coulomb barrier separating 2 protons amounts to roughly 1 mega-electronvolt. To overcome this classically, the protons would need kinetic energies corresponding to a temperature of approximately 3 billion degrees. The core of the Sun sits at about 15 million degrees. That is roughly 200 times too cold. Think about what this means. If classical physics were the complete description of reality, fusion in the solar core would be impossible. Every proton collision would end in repulsion. No helium would form. No energy would be released. The Sun, along with every other main sequence star in the universe, would be nothing more than a ball of hot, inert hydrogen, slowly cooling into darkness. Every night sky would be black. Every solar system would be lifeless. The universe would contain matter, gravity, and cold, and nothing else. The resolution arrived just 1 year after Gamow's tunnelling paper, and it came from 2 relatively obscure physicists whose names rarely appear in popular science. In 1929, Robert Descour Atkinson, a Welsh astronomer, and Fritz Houtemans, a German physicist, published a calculation that changed everything. They took Gamow's tunnelling factor, the same exponential formula that had explained alpha decay, and applied it to the conditions inside a star. Their conclusion was direct. At the temperatures and densities found in stellar cores, hydrogen nuclei could penetrate the Coulomb barrier through quantum tunnelling. Fusion was not impossible. It was improbable on a per-collision basis, but it was physically real, and the sheer number of collisions in a stellar interior made the improbable inevitable. Atkinson and Houtemans had opened the door, but it was Hans Bethe who walked through it and mapped every room. Working at Cornell University in the late 1930s, Bethe laid out the precise nuclear reaction chains that power the Sun. The dominant process, responsible for roughly 99% of the Sun's energy, is the proton-proton chain. It begins with the simplest possible fusion event. Two protons collide and combine to form a deuterium nucleus, one proton bound to one neutron. This is where tunneling does its essential work. Two protons, each carrying thermal energies measured in kilo-electron-volts, far below the mega-electron-volt Coulomb barrier, approach each other and through quantum tunneling get close enough for the nuclear force to bind them. But tunneling alone is not enough. There is a second bottleneck, one that is rarely discussed outside specialist physics, and it makes the Sun's existence even more remarkable. During the fleeting instant when two protons are close enough to feel each other's nuclear force, one of them must spontaneously undergo a weak force decay. It must convert from a proton into a neutron, emitting a positron and a neutrino in the process. This is a beta plus decay governed by the weak nuclear interaction, the feeblest of nature's fundamental forces. The probability of this happening during the vanishingly brief moment of nuclear proximity is extraordinarily small. So the first step of the proton-proton chain faces a double bottleneck. The protons must tunnel through a barrier they classically cannot cross. And during the instant they are together, one must undergo a decay so rare that it almost never happens. These two improbabilities, layered on top of each other, throttle the fusion rate to a degree that is difficult to overstate. And this is precisely why the Sun is stable. It does not detonate. It does not exhaust its fuel in a violent flash. The fusion rate on a per-proton basis is so astonishingly low that the Sun will continue burning hydrogen for another 5 billion years. A single proton in the solar core will wait, on average, roughly 10 billion years before it successfully fuses with another proton. That is longer than the Sun has existed. The double bottleneck is not a flaw in the design. It is the thermostat. It is the reason stars burn gently for billions of years rather than detonating like bombs. Bethe's work laid all of this bare, and it earned him the Nobel Prize in 1967. The warmth on your face on a clear afternoon, the photosynthesis that sustains every plant on this planet, the light from every star you have ever seen on a winter night, all of it depends on a quantum mechanical event so unlikely that any individual proton-proton collision has essentially no chance of succeeding. The Sun works not because tunneling is probable, but because the Sun contains so unfathomably many protons that the improbable becomes, across the whole core, absolutely certain. Which leads to a natural question. If individual collisions are so unlikely, where exactly does the fusion happen? Not at what temperature? At what energy? The answer is one of the most elegant ideas in stellar physics. It is called the Gamow peak. Inside the Sun's core, protons carry a range of kinetic energies described by the Maxwell-Boltzmann distribution. Most sit near the average, with modest thermal energy. A smaller number carry significantly more. And a tiny, rapidly declining tail stretches out to very high energies. The hotter the gas, the fatter this tail becomes. But even in the Sun's core, most protons are moving far too slowly to have any real chance of tunneling through the Coulomb barrier. Now, tunneling probability increases with energy. A proton carrying more kinetic energy approaches a thinner effective barrier and has a better chance of getting through. So you might expect that fusion is dominated by the fastest protons, the ones sitting far out on the high-energy tail of the distribution. But here is the catch. The number of protons at any given energy drops exponentially as you move further along the tail. The faster you go, the fewer protons there are. So you have two competing effects. Tunneling probability rises with energy. The population of available protons falls with energy. Both relationships are exponential, and they pull in opposite directions. Where these two curves overlap, where the rising tunneling probability meets the falling particle population, there is a narrow window, a sweet spot. This is the Gamow peak. For proton-proton fusion in the Sun, it sits at roughly 6 kilo-electron-volts. That is about 6 times the average thermal energy of a core proton, but still far, far below the 1 mega-electron-volt Coulomb barrier. Fusion does not happen at the barrier. It does not happen at the average temperature. It happens in this precise narrow band where the mathematics of probability and quantum mechanics intersect. The Gamow peak is remarkably slim. Only a tiny fraction of protons, roughly 1 in every million at any given instant, carry energies within this window. But the Sun's core is vast, dense, and busy. Protons collide at frequencies exceeding 20 terahertz. Multiply a vanishingly small probability by an incomprehensibly large number of attempts, and the result is a steady output of 400 trillion watts. The Sun does not need every collision to succeed. It needs enough of them, and tunneling through the Gamow peak ensures that enough of them do. There is a deeper elegance here too. The Gamow peak is not just a window, it is a self-regulating mechanism. If the core heats up, the peak shifts, fusion accelerates, the core expands slightly, and the temperature drops back down. If the core cools, the peak shifts the other way, fusion slows, the core contracts under gravity, and the temperature rises. The star is held in balance, decade after decade, century after century, for billions of years, by the interplay between gravity, thermal energy, and the quantum mechanical probability of tunneling through a barrier that classical physics says cannot be crossed. For 3 decades after Gamow's breakthrough, quantum tunneling remained a phenomenon of the nucleus and the star. It was understood, it was calculated, it was accepted, but it had not yet been harnessed. Nobody had built anything with it. Nobody had turned the mathematics into a device you could hold in your hand. That changed in a laboratory in Tokyo in the autumn of 1957. Ryo Esaki was a young physicist working at Tokyo Tsushin Kogyo, the company that would soon rename itself Sony. He was studying semiconductor junctions, investigating what happened when you pushed electrical current through a germanium diode. Most diodes behave predictably. Increase the voltage and the current increases. The relationship is smooth, well understood, and entirely classical. But Esaki had constructed something different. He had doped his germanium so heavily with impurities that the barrier region between the two semiconductor layers had become extraordinarily thin, about 10 nanometers across, a few dozen atoms wide. At that thickness, something unexpected happened. Electrons did not need to climb over the energy barrier separating the two sides of the junction. They tunneled through it, and the result was a current voltage curve that no classical model could reproduce. As Esaki increased the voltage, the current first rose, then fell, then rose again. That dip, the region where increasing voltage produced decreasing current, is called negative resistance, and it was the unmistakable signature of quantum tunneling in a solid-state device. Esaki had built the tunnel diode, the world's first quantum electronic component. The response was not the immediate recognition you might expect. When Esaki presented his results, the reaction from parts of the physics community was cautious. The work challenged comfortable assumptions about semiconductor behavior, and some found it difficult to accept that a quantum phenomenon previously confined to nuclear physics and astrophysics was now operating in a tabletop device made of germanium. But the data was clear, the negative resistance was reproducible, and the physics, once examined carefully, was sound. Recognition when it came was unequivocal, but it did not come alone. In 1960, Ivar Giæver, a Norwegian-American physicist working at General Electric in Schenectady, New York, demonstrated something equally remarkable. He showed that individual electrons could tunnel through a thin insulating layer sandwiched between a normal metal and a superconductor. This was not simply a repetition of Isaki's work in a different material. It was a direct window into one of the most important theories in condensed matter physics. The BCS theory of superconductivity, developed by John Bardeen, Leon Cooper, and Robert Schrieffer, predicted that below a critical temperature, electrons in a superconductor form bound pairs, called Cooper pairs, and that an energy gap opens up in the material's electronic structure. Giæver's tunnel junction let physicists measure that gap directly. A theoretical prediction became a number you could read from an instrument. Tunneling had turned into a precision tool for probing the quantum structure of matter. 2 years after Giæver's experiment, the story took another turn. Brian Josephson was a graduate student at Cambridge when he predicted something that startled even his supervisors. He showed mathematically that Cooper pairs could tunnel coherently through a thin insulating barrier separating two superconductors. Not one electron at a time, not as individual particles losing their quantum identity in transit, but as bound pairs, preserving their phase relationship across the gap. The supercurrent that flowed required no applied voltage. It simply existed, carried by pairs of electrons tunneling in lockstep, their quantum mechanical wave functions reaching through the barrier and connecting on the other side. The Josephson effect, as it became known, was confirmed experimentally within a year. Its precision turned out to be almost absurd. A Josephson junction responds to applied voltage with an oscillating current whose frequency is proportional to the voltage with extraordinary accuracy. So accurate, in fact, that the international standard for the volt is now defined through the Josephson effect. The same junctions can detect magnetic fields 1 billion times weaker than the Earth's, forming the heart of devices used in medical brain imaging and geological surveys around the world. In 1973, Leo Esaki, Ivar Giæver, and Brian Josephson shared the Nobel Prize in Physics. 3 physicists, 3 different materials, 3 different manifestations of quantum tunneling in solids recognized together. In barely 15 years, tunneling had gone from a theoretical explanation of nuclear decay to the operating principle of electronic devices, precision measurement instruments, and an entirely new way of investigating the quantum properties of matter. But the most visually dramatic consequence of tunneling was still ahead, and it began with a deceptively simple question. Could you use the tunneling current between a sharp tip and a flat surface to build an image? Not an image made of light, an image made of atoms. In the late 1970s, at IBM's Zurich Research Laboratory in Switzerland, 2 physicists started pursuing exactly this idea. Gerd Binnig and Heinrich Rohrer, working alongside their colleague Christoph Gerber, wanted to build a microscope that used quantum tunneling as its imaging mechanism. The principle was almost recklessly direct. Take a conducting tip, ideally sharpened so finely that a single atom sits at its apex. Bring it within a few angstroms of a surface. At that distance, electrons tunnel between the tip and the sample. The tunneling current depends exponentially on the width of the gap. Move the tip 1 angstrom further away, roughly 1/10,000,000th of a meter, and the current drops by approximately an order of magnitude. That exponential sensitivity is the entire instrument. By scanning the tip across the surface and monitoring the tunneling current, you can map the atomic landscape beneath it. Every bump, every valley, every individual atom on the surface registers as a change in the current. The Scanning Tunneling Microscope, or STM, does not bounce light off a surface. It feels it, atom by atom, through the quantum mechanical leakage of electrons across a gap that no classical current could cross. The first clear exponential tunnel signal came on the night of the 16th of March, 1981. Koenig later described the experience of seeing those first images as entering a new world. And the phrase was not hyperbole. For the entire history of science up to that point, atoms had been inferred, calculated, modelled and theorised about, but never directly seen in this way. The STM changed that. Individual atoms on a surface were no longer abstractions in a textbook. They were visible, mappable, countable. Skepticism lingered in parts of the community. Some physicists questioned whether the images represented genuine atomic structure or artifacts of vibration, contamination or noise. The turning point came in 1983, when Koenig and Rohrer resolved the silicon 7x7 surface reconstruction, a complex rearrangement of atoms on a silicon crystal face that had been predicted theoretically but never directly observed. The STM images matched the predictions with extraordinary clarity. The debate was over. The instrument was real, and so were the atoms it revealed. To appreciate the scale of what the STM accomplished, consider its resolution. Better than 1 angstrom laterally, roughly 1/100th of a nanometer in depth. That is sensitive enough to distinguish between the top of an individual atom and the gap between two neighbouring ones. No optical microscope can approach this. Visible light has a wavelength hundreds of times larger than the features the STM resolves routinely. By building an instrument whose entire operating principle rests on the exponential sensitivity of quantum tunneling, Koenig and Rohrer had made visible what light itself could not reveal. The Nobel Prize came in 1986, just 5 years after the first tunnel signal. It was one of the shortest gaps between invention and Nobel recognition in the history of the prize, and it reflected the sheer breadth of what the STM had opened up. Surface science, materials science, semiconductor physics, molecular biology, all of them were reshaped by the ability to see and probe matter at the atomic scale. But the demonstration that lodged most firmly in the public imagination came 4 years after the Nobel. In 1990, at IBM's Almaden Research Center in California, Donald Eigler and Erhard Schweitzer used a scanning tunneling microscope not just to image atoms, but to move them, one at a time. They positioned 35 individual xenon atoms on a nickel surface, nudging each one into place with the STM tip, and arranged them to spell out 3 letters, IBM. The image was published and went around the world. It remains one of the most recognized photographs in the history of science, not because of what it shows, but because of what it proved. Individual atoms could be picked up and placed with precision. Matter could be assembled from its most fundamental components, one atom at a time. The theoretical possibility had become a physical demonstration, and it announced, more clearly than any paper or equation could, that humanity had learned to build at the smallest scale nature allows. There is a good chance you are listening to this on a device whose memory depends entirely on quantum tunneling, not as a metaphor, not as a loose analogy. The ones and zeros stored in every flash drive, every solid-state hard drive, every smartphone you have ever owned, are written and erased by electrons passing through barriers they classically should not be able to cross. Flash memory stores data by trapping electrons on a tiny island of conducting material called a floating gate. This gate sits inside a transistor, isolated from the rest of the circuit by a thin layer of insulating oxide just a few nanometers thick. Whether or not the floating gate holds a charge determines whether the transistor reads as a 1 or a 0. That is your data. Billions of ones and zeros, billions of tiny electron prisons, each one written by tunneling. To store a bit, a voltage is applied across the oxide layer. The electric field distorts the shape of the energy barrier from a flat rectangle into a sloping triangle, thinning it at one end. This is Fowler-Nordheim tunneling, a distinct mechanism from the square barrier tunneling that governs alpha decay, or the STM. The triangular barrier is thin enough for electrons to pass through at a usable rate. They tunnel into the floating gate and stay there, trapped, holding their charge, even when the power is switched off. To erase, the process is reversed. A voltage in the opposite direction pulls the electrons back out through the oxide by the same tunneling mechanism. The concept has a longer history than you might expect. In 1967, Dawon Kang and Simon Zhe, working at Bell Labs, proposed the idea of a floating gate transistor as a memory element. The notion sat largely dormant for 2 decades. Then, in 1988, engineers at Toshiba developed the NAND flash architecture, a practical, commercially viable design that could pack enormous numbers of floating gate cells onto a single chip. That architecture is the foundation of virtually all solid-state storage manufactured today. A single modern flash chip can hold trillions of bits. Every one of them is written by quantum tunneling. But tunneling is not only the mechanism that makes flash memory possible, it is also the mechanism that threatens to make it impossible. As transistors have shrunk over decades of relentless miniaturization, the insulating layers separating components have grown thinner and thinner. This has been the engine of progress in computing. Smaller transistors mean more transistors per chip, more processing power, lower cost, greater speed. But there is a flaw, and it is set by quantum mechanics. Below roughly 1 nanometer of insulator thickness, electrons begin to tunnel through the barrier even when no voltage is applied. They leak. This leakage wastes power, generates heat, and can corrupt the very data the device is meant to store. The same phenomenon that writes your information threatens to destroy it if the walls between components become too thin. This is not an abstract concern for some distant future. Modern processors contain transistors with features measured in single-digit nanometers. The oxide layers are approaching the tunneling threshold. The semiconductor industry has invested billions in engineering around this limit, replacing traditional silicon dioxide insulators with exotic high dielectric constant materials, redesigning transistor geometries from flat structures into 3-dimensional fins, exploring entirely new architectures. But the underlying physics does not negotiate. Tunneling cares about barrier width and particle mass. It does not care about your fabrication budget. Out of this constraint has grown an entirely new direction in electronics. The tunnel field effect transistor does not try to suppress unwanted tunneling. It embraces it. Instead of controlling current by raising and lowering a voltage barrier in the conventional way, it controls the rate at which electrons tunnel through a barrier at the device's junction. The approach promises dramatically lower power consumption and the potential to push miniaturization past the limits of conventional designs. What started as an obstacle is being reimagined as an operating principle. The same quantum effect that places a flaw under one technology is becoming the foundation of the next. Everything discussed so far, the alpha particle escaping uranium, the proton fusing in the sun, the electron tunneling through a germanium junction, or an oxide layer, involves particles so small that their quantum nature is expected. Electrons have negligible mass. Protons are tiny. Alpha particles are among the lightest composite objects in nature. At these scales, wave functions, probability distributions, and tunneling are the default description. The classical world, the world of definite positions and solid barriers, is the exception, not the rule. But there is a question that has shadowed quantum mechanics since its earliest days. A question that is easy to ask and extraordinarily difficult to answer. Does it stop? Is there a size, a mass, a scale beyond which quantum tunneling simply ceases to operate? A boundary where the wave-like description of matter gives way and the solid deterministic classical world reasserts itself? Or does quantum mechanics, in principle, apply to everything, from a single proton to a planet, with no upper limit at all? Anthony Leggett, a British-American theoretical physicist, spent years thinking about this question with unusual precision. In the early 1980s, he proposed a specific, testable thought experiment made real. Take a superconducting circuit containing a Josephson junction, the same thin insulating barrier that Brian Josephson had described 2 decades earlier. In such a circuit, the quantum variable is not a single electron. It is a collective state, a current carried by billions of Cooper pairs, all moving together in lockstep. Leggett argued that if quantum mechanics truly has no upper size limit, then this macroscopic current should be able to tunnel between 2 distinct energy states, just as a single electron tunnels through a thin barrier. The idea was striking in its ambition. Not a single particle, not a handful. Billions of particles, acting as one quantum object, tunneling collectively through an energy barrier. It was, in essence, a direct test of whether the rules that govern protons also govern things you can see and hold. The experiment was carried out in 1984 and 85 at the University of California, Berkeley. John Clark, Michel Devoret, and John Martinez built a superconducting circuit with a Josephson junction and cooled it to millikelvin temperatures, thousandths of a degree above absolute zero. At these temperatures, thermal noise effectively vanishes. Any transitions between energy states can be attributed to quantum effects rather than random thermal fluctuations. What they measured was definitive. The rate at which the circuit switched between energy states did not match classical thermal activation. It matched quantum tunneling. The superconducting circuit, a macroscopic object containing billions of Cooper pairs, was tunneling between quantum states as if the entire system were a single particle encountering a barrier. The wave function of the circuit's collective state was doing precisely what Schrödinger's equation predicted. It was leaking through. They found more. The circuit did not simply tunnel. It absorbed and emitted energy in discrete quantized amounts, another signature of quantum behavior that no classical system exhibits. The energy levels were sharp and well defined. Macroscopic quantum tunneling was not a theoretical possibility. It was measured, recorded, and published. Leggett received the Nobel Prize in 2003 for his theoretical work on quantum phenomena in macroscopic systems. Clark, Devoret, and Martinez received theirs in 2025, awarded specifically for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. Between the prediction and the recognition, 4 decades passed. Between the experiment and the technology it enabled, the line is direct and unbroken. Those superconducting circuits, cooled to near absolute zero, tunneling between quantized energy states, are the direct ancestors of the superconducting qubits used in quantum computers today. When a qubit in a machine built by Google or IBM processes information, it exploits the same physics that Clark Deverett and Martinis first measured in a basement laboratory in Berkeley. The quantum bit exists in a superposition of states, and the transitions between those states are governed by tunneling through energy barriers within the circuit. Quantum computing did not emerge from a single eureka moment. It grew, step by careful step, from an experiment designed to answer one of the oldest questions in quantum physics. Can something large enough to hold in your hand behave like a quantum particle? The answer, confirmed in a cryostat in California and recognized in Stockholm 4 decades later, is yes. The story so far has moved from the nucleus to the star, from the laboratory to the smartphone, from the single electron to the macroscopic circuit. Each step has stretched the reach of tunneling further into territories its discoverers never anticipated. But there is one more arena, and it shifts the implications from the physical to the biological, from the cosmic to the personal. In 1963, a Swedish quantum chemist named Per-Olof Lövdin proposed something quietly extraordinary. He had been thinking about DNA, specifically about the hydrogen bonds that hold the 2 strands of the double helix together. These bonds are maintained by protons sitting in precise positions between pairs of nucleotide bases. Adenine bonds to thymine, guanine bonds to cytosine. The exact position of the proton in each hydrogen bond determines which base pairs with which, and therefore what genetic information that section of DNA encodes. Lövdin's proposal was simple in outline and profound in implication. Those protons, he suggested, could tunnel, not across large distances, not through thick barriers, but across the small energy barrier separating the proton's normal, stable position from a slightly shifted alternative called a tautomeric form. In the tautomeric configuration, the base changes its bonding preference. It looks, chemically, like a different letter. During DNA replication, when the double helix unzips and each strand serves as a template for a new partner, a base sitting in its tautomeric form can pair with the wrong partner. The copying machinery reads the shifted base as something it is not, and the result is a point mutation. A single letter error in the genetic code, introduced not by radiation, not by a chemical mutagen, not by any external damage, but by the quantum mechanical behavior of a proton. The idea was decades ahead of the tools needed to test it. Lövdin lacked the computational power to model proton dynamics within a DNA base pair at the quantum level. His proposal sat in the literature, acknowledged by a few specialists, largely ignored by the broader scientific community, waiting for the rest of physics and chemistry to catch up. The wait lasted nearly 60 years. In 2022, a team at the University of Surrey published a study that brought Lövdin's idea into sharp quantitative focus. Jim Al-Khalili and Marco Sacchi, working within the Leverhulme Quantum Biology Doctoral Training Centre, used quantum mechanical simulations to model proton behaviour inside DNA base pairs with a level of detail that had simply not been possible before. Their results were striking. Quantum tunnelling contributed to proton transfer rates at levels orders of magnitude higher than classical thermal hopping alone. The protons were not just occasionally nudged into tautomeric positions by random thermal energy. They were tunnelling there, passing through the energy barrier rather than climbing over it, at rates that made the process far more common than anyone had previously calculated. Their work suggested that at any given moment, hundreds of thousands of tautomeric forms may exist across a cell's genome. Not one or two, not a handful scattered among billions of base pairs. Hundreds of thousands, constantly forming and reverting, a quiet, ceaseless quantum shimmer running through the code of life. Most of these are corrected before they cause any harm. The cell's own repair machinery is remarkably efficient at catching and fixing errors. But some slip through, and those that slip through are mutations. There is a beautifully direct piece of experimental evidence supporting this picture. When the hydrogen atoms in DNA are replaced with deuterium, a heavier isotope of hydrogen that carries an extra neutron in its nucleus, the rate of spontaneous mutation drops. Deuterium is approximately twice the mass of ordinary hydrogen, and heavier particles tunnel less efficiently. The exponential dependence on mass that governs all tunneling means that doubling the particle's mass dramatically reduces the probability of barrier penetration. If mutations were caused purely by classical thermal vibrations, by protons simply being jostled over the barrier by heat, then the isotope substitution should make relatively little difference. The thermal energy is the same regardless of which isotope is present. The fact that heavier hydrogen measurably reduces the mutation rate, a result consistent with what physicists call the kinetic isotope effect, points directly and specifically to tunneling as part of the mechanism. The implications reach beyond DNA itself. Enzymes, the molecular machines that catalyze virtually every chemical reaction in living cells, also exploit tunneling. Judith Klinman, working at UC Berkeley, and Nigel Scrutton at the University of Manchester have spent years demonstrating that proton and electron tunneling within enzyme active sites contributes meaningfully to reaction rates. The enzymes do not merely lower the energy barrier for a reaction, which is the classical description of catalysis. They create geometries, distances, and electrostatic environments where tunneling becomes a significant part of the reaction pathway. Rates that classical transition state theory cannot fully account for become explicable once tunneling is included in the calculation. Stand back far enough, and the picture is almost surreal in its scope. The same quantum phenomenon that allows an alpha particle to escape a uranium nucleus, that powers the fusion reactions at the heart of every star in the observable universe, that writes data onto a flash drive and reads a surface atom by atom, that was confirmed at macroscopic scale in a superconducting circuit in Berkeley. That same phenomenon is operating right now inside cells throughout your body. Protons in your DNA are tunneling between configurations, occasionally producing tautomeric forms, occasionally slipping past the repair machinery, occasionally becoming mutations that alter the instructions your cells follow. The process that lights the sun is editing the letters of your genetic code. Quantum tunneling is not a closed chapter. It is not a phenomenon whose boundaries are fully mapped and whose surprises are exhausted. Some of its most fundamental questions remain unanswered, and active research programs around the world are pushing it into territories that Gamow, Esaki, and Binig could not have imagined. The most stubborn open question is disarmingly simple to state. How long does tunneling take? When a particle passes through a barrier, does it spend time inside? And if it does, how much? The question sounds straightforward, but it has generated decades of debate and no consensus. For years, certain theoretical calculations and experimental results appeared to suggest that tunneling could be instantaneous or even superluminal, that particles emerged from the far side of a barrier faster than light could have crossed the same distance through empty space. If true, this would have implications reaching far beyond tunneling itself, touching the foundations of relativity and our understanding of causality. Information travelling faster than light would upend physics as we know it. Herbert Winful, a theoretical physicist, offered a different reading of the data. The apparent superluminal speeds, he argued, do not represent a particle racing through the barrier at impossible velocity. They arise from a subtlety in how group velocity behaves in evanescent waves, the decaying wave functions inside the barrier. The measurement is real. The interpretation, Winful contended, was wrong. The particle is not outrunning light. The nature of the measurement itself is more delicate than it first appears. In 2020, Ephraim Steinberg and his group at the University of Toronto carried out what may be the most direct measurement of tunneling time yet attempted. Using a technique called Larmor precession, they effectively gave atoms an internal clock, a spin that rotated at a known rate, allowing them to measure how long the atoms spent inside a barrier during the tunneling process. Their results suggested that tunneling is not instantaneous. Particles do spend a finite, measurable amount of time inside the barrier. But the interpretation remains contested among physicists, and the deeper question, what tunneling time truly means at a fundamental level, has not been settled. Far from any laboratory, in the coldest and emptiest regions of the universe, tunneling is quietly reshaping our understanding of chemistry itself. In interstellar space, where temperatures hover just a few degrees above absolute zero, chemical reactions should be impossible by any classical measure. The thermal energy available to molecules at those temperatures is so negligible that even the lowest activation barriers should block every reaction pathway. Molecules should not form. Complex chemistry should not exist, and yet it does. Water ice, methanol, formaldehyde and other compounds, some of them essential precursors to the chemistry from which life eventually arose, are found in these frigid molecular clouds. Their existence has puzzled astrochemists for years. In 2023, a team at the University of Innsbruck used a precision ion trap experiment to measure the rate of a tunneling-assisted chemical reaction at temperatures approaching absolute zero. They found that roughly one collision in every 100 billion produced a successful reaction. That rate is vanishingly small by everyday standards, but it is orders of magnitude higher than any classical model predicts for those temperatures. Tunneling was enabling chemistry in conditions where no chemistry should be possible. The implication is remarkable. Some of the molecular building blocks of life may owe their existence not to heat, not to violent stellar forges, but to the patient, persistent leaking of wave functions through energy barriers in the coldest, quietest corners of the cosmos. And there is the question of scale. The 2025 Nobel experiments demonstrated quantum tunneling in a superconducting circuit, a macroscopic object. But where is the true ceiling? Single molecule magnets have been shown to exhibit quantum tunneling of their magnetic moment, the entire magnetic orientation of a molecule flipping from one state to another by passing through a barrier rather than climbing over it. Theoretical work continues to probe whether still larger systems, under precisely the right conditions, might tunnel. The boundary between the quantum world and the classical one, if such a boundary exists at all, has not yet been found. Every time physicists have looked for it, they have found quantum mechanics still operating, quietly, reliably, at scales previously assumed to be too large. There is a particular kind of strangeness to living in a universe where barriers are not absolute. We experience walls as solid. We experience limits as real. Every intuition we carry tells us that a boundary is a boundary, that what lacks the energy to cross it remains on the side where it began. At the scale of our daily lives, this is perfectly true. The coffee cup on your desk will not tunnel through the table. The door you closed this morning will not spontaneously find itself open. Classical physics holds, reliably and completely, at the scale of everything you can see. But beneath this predictable surface, something else has been happening since long before anyone was here to notice. Protons inside atomic nuclei are tunneling through Coulomb barriers at this very moment, keeping radioactive decay ticking at precisely the rates the universe requires. Deep within the core of the Sun, and within every star visible on a clear night, protons are slipping through barriers 200 times higher than their energy permits, fusing hydrogen into helium, releasing the light that crosses the void and reaches this particular planet. In the flash memory of the device in your pocket, electrons are tunneling through oxide layers a few atoms thick, encoding and erasing the information your life runs on. In laboratories around the world, tungsten tips are hovering angstroms above surfaces. They're tunneling currents tracing the positions of individual atoms that no beam of light could ever resolve. In superconducting circuits cooled to temperatures colder than the emptiest reaches of interstellar space, billions of particles are tunneling as one, their collective quantum states forming the qubits of a technology that has never existed before. And inside you, right now, protons in the hydrogen bonds of your own DNA are shifting between configurations, tunneling from one position to another, occasionally producing a tautomeric form that will, if unrepaired, become a permanent change in the next copy of your genetic code. The same phenomenon. Every one of these processes. The same mathematics, the same exponential dependence on barrier width and particle mass. The same wave function leaking through a wall that classical physics insists is solid. George Gamow, sitting in Göttingen in the summer of 1928, could not have known where his mathematics would lead. He was solving a specific puzzle about alpha decay, trying to understand why uranium emitted particles carrying half the energy the barrier demanded. What he found, and what Gurney and Condon found independently one day later, was not just the answer to that question. It was a principle woven so deeply into the structure of the physical world that nearly a century of discovery has not exhausted its reach. Stars, atoms, microscopes, memory chips, DNA, quantum computers. The thread runs through all of them, unbroken. There is something quietly extraordinary about a universe that operates this way. A universe where the barriers that seem most solid are, at the deepest level, permeable. Where the impossible is not truly impossible, but merely improbable, and where improbability, given enough time or enough particles, becomes certainty. We live our lives on the classical side of this divide, in a world where walls are walls and locked doors stay locked. But everything that makes that world possible, the stars that light it, the atoms that compose it, the biology that animates it, depends on a reality where the rules are different, where a wave function does not stop at a wall, where a proton can be here and then, without ever crossing the space between, be there. The barrier is real. It has a height, a width, a measurable resistance to anything that tries to pass. But the passage through it is equally real. And the universe, it turns out, has always known the difference.